Hi folks, today's video is about pressure in liquids. And the key idea here is that the gap between the particles that make up a liquid is very small, and therefore liquids cannot be compressed. Therefore, they transmit pressure. And the idea can be seen with this in the particle picture of a liquid. If you consider a solid, say for instance, this particle will always be enabled with this particle, will always be enabled with this particle. There's no real gaps between the particles, so when you try and compress it, they can't be compressed. With a liquid it's slightly different. The particles are separated by approximately the same distance, but the neighbours continually change. That's the key difference between a liquid and a solid. Because there's no real gaps between the particles, liquids are very, very difficult to compress. That's totally different to a gas. You can see that the average distance between the particles of a gas is quite large, and so gases can be compressed. If you get a lemonade bottle, you put the top on and you try and compress it, you can see it can be compressed quite a lot. If the pressure in a liquid is the result of the weight of a liquid over an area. So if I look at this example whereby I've got water in a container, say a beaker, if I consider the area at the bottom, this area at the bottom, well, what's going to happen is all of this water here, above it, all of it, right the way up to the top, all of that water is going to have a weight, and that weight is going to push it down over that area. So I can say the pressure underneath this area here is P is equal to the weight of all that water that I've highlighted here, divided by the area at the bottom. Now, this pressure acts normally to this surface, so I think that's a very important notion, the fact that it acts normally, and extremely important, it acts in all directions. That isn't obvious at first. When I say it acts normally, that means if the surface is like that, pressure acting normally just means at an angle of 90 degrees to the surface, so that's what we mean when we say normally. The idea of all directions, it's pretty obvious that at the bottom there's going to be a pressure normally against that surface. The weight of the liquid does act down. But it also acts against the surface of the side of the container. And at the top it acts, but the pressure is less because there's less weight of the weight of the water here isn't as much. So essentially what happens is it acts in all directions, and it gets progressively greater as you go down against all surfaces. Now, why does it act in all directions? I think the reason why it acts in all directions can be best answered by considering this picture, this particle picture. If I push down on this particle here, well, what that's going to do is it's going to push down on this particle here. And what that's going to do is if that particle goes down, this particle gets pushed to the side, which means that this particle gets pushed up, and I suppose this particle kind of gets pushed in that direction here. The fact that pressure is transmitted in all directions in a liquid suggests to us just how small the particles which make up the liquid are. The evidence for pressure acting in all directions can be seen from the spouting can experiment. If I have a can full of water and I punch some holes in it, one thing will happen. What will happen is the water will come out the side, so it will come out a little bit at the top, it will come out a bit more in the middle, and it will come out a lot at the bottom. This tells us two things. It tells you that the further down that you go in the water, in other words, as H increases, this depth increases, well, the pressure gets greater because the water is being pushed out more. But the second thing that it shows us is that pressure is actually acting in all directions. If the pressure only acted down, it would be impossible for the water to be forced out the side. And you can quite clearly see that it will be forced out the side. The equation that you need to know for pressure at a depth is the pressure at a depth is given by rho g h. Rho is the density of the liquid, g is the gravity of the planet that you're on, and h is the depth of the water that you're in. Now, this is really just a reworking of the equation that we had earlier on, which is the weight of a fluid over whatever area it's pushing down over. But this is the easier one to use. Now, it's important that when you're using that equation, that you realise that rho, the density, must be measured in kilograms per metre cubed, and the height must be measured in metres, and the gravity must be measured in, well, the acceleration of gravity, metres per second squared. If you use all of those units, well, then the pressure you will get out is pascals, and you know that 1 pascal is equal to 1 Newton per 1 metre squared. Okay, that's the video. Thank you.